Hello, my name is Patrick Bahr and I'm presenting joint work with my colleagues Graulund and Rasmus Møgelberg from the IT University of Copenhagen. In this paper we present a functional reactive programming language that combines guarded recursion with inductive types that can be used to express liveness properties. But before I get into that, let me say a few words about reactive programming. So you can think of a reactive program as a piece of software that runs indefinitely, and while doing so it interacts with some kind of environment. So it receives input from the environment and produces output to the environment. So you can think of, for example, a GUI that a user interacts with, or a server that a client can connect to, or a piece of control software that interacts with some machinery consisting of sensors and actuators. So let's say a self-driving car or a robot or a nuclear reactor. So many safety critical systems are in fact an instance of this kind of architecture of reactive software. So we really want to make sure that these run as expected and don't crash and don't cause failures. However, traditionally these have been implemented in an imperative style, and still are to this day implemented in an imperative style often, which means that they react to inputs, so from external events, using callbacks, register callbacks, and then these callbacks will manipulate some kind of shared state. So they will read from the shared state and then write back changes to the shared state. And it's very difficult to understand what this kind of software will do. And so if you get a piece of code that is written in this style, it's very difficult to understand what's going on. So this is very difficult to reason about these kind of programs, and therefore they are very much prone to errors. So what we want to do instead is to program these kind of systems in a functional style. So we want to use high-level abstractions to program reactive systems. We want to program them in a modular fashion and want to be able to express safety guarantees using types. As an example, let's say we want to write a very simple reactive program that receives some signal of natural numbers and then wants to count how many times do we see a positive number. So then produces a signal of natural numbers that is the number of times we've seen a positive number. Right, and it does so by using a higher order function that checks each of the incoming numbers whether it's bigger than 0, and if so produces a value true, and then it composes this function with another function count true that receives that signal of Boolean values and produces a signal of natural numbers. And then you can implement this count true function separately, which simply counts the number of times it sees the value true. And so it's much easier to understand what's going on here. There's no shared state. You can understand the components individually. So this is the style of programming advocated by functional reactive programming, where you program in a functional style with signals. Now you can think of signals as simply being values that vary over time. Right? So, and then reactive programs themselves are simply functions that manipulate these signals. So these are signal transducers, meaning they take signal as input, signal of type A, and produce signal as an output here, signal of type B. So going back to the picture I've showed you earlier, we have our reactive program that interacts with the environment by receiving a signal of type A and producing a signal of type B. And one sort of straightforward way of encoding such signals is as a stream. Right? So you think of a signal of type A being a head of the stream and a tail of the stream, which is then the continuation of this signal. And we just call this type a stream. And this is very convenient to work with. It's really nice to work with this in a functional style. The problem being, though, is that if you do so in a straightforward way, you can implement functions that are not causal and not productive. And furthermore, you can also program functions that leak memory, right? So that you over time use more and more memory, which is especially problematic for reactive software that runs indefinitely. So this will just grind to a halt eventually. So what we do in this work is we present the functional reactive programming language Lively RaTT, which is the first such language that combines these four properties in one language. It avoids implicit space leaks, so there's no way of retaining memory over time. You have to do so explicitly. All programs are causal, which essentially means that programs are implementable in a reactive style. All programs are productive, so they cannot get stuck, for example, by running into an infinite loop. And lastly, we can express liveness properties such as termination or fairness using inductive types. So the first three were already covered in previous work by Krishnaswamy in 2013 and in our earlier work from 2019. And both of these use guarded recursion. So they then ensure these three properties. In 2014, Cave and colleagues also presented a calculus that, while not necessarily ensuring the absence of space leaks, they ensure causality and productivity and also allow us to express liveness properties using inductive types. So the main contribution of this work is extending this previous line of work based on guarded recursion with the ability to express liveness properties. And so the main technical challenges that we faced in this endeavor was how to integrate inductive types with guarded recursive types, which has been an open problem so far. And secondly, we also had to actually prove that the resulting system allows us to express liveness properties using inductive types, which is a challenge in itself because usually you use step-index logical relations to prove these safety properties. But so far, they have not been used to also prove liveness properties. So we'll see how we achieve that. Okay, so let me say a few words about how these kind of function-active programming languages work. So they're based on a modal style of function-active programming that goes back to Jeffrey and Ejlers and Krishnaswamy from 2012 and 13. So the idea is that we borrow the later modality from temporal logic. And the idea is that whenever we have a value of type later A, this is a computation that one time step from now will give us a value of type A. So now instead of working with normal streams, we work with guarded streams. Right? So here, importantly, the tail of the stream is guarded by the later modality. So a stream is now the head of the stream now and the tail of the stream later. So this is then combined with guarded recursion. So the idea is to add a guarded fixed point combinator fix that takes a function of type later A to produce a fixed point of type A. So the way that this works is that we essentially equate the circle modality from temporal logic with the triangle modality from guarded recursion that is usually used in this guarded fixed point combinator. There's a nice coincidence of this kind of temporal aspect of the circle modality and the logical aspect of the triangle modality. And as a result of this, we can actually ensure that programs are indeed causal, productive, and avoid implicit space leaks. Then the question becomes, how do we introduce inductive types to such a language? Right? So how can we express an inductive type like this diamond A that expresses the promise that we get a value of type A sometime in the future. Like, for example, we would like to have a server of the following type that says, let's give it a request now, and then the server will respond with a result sometime in the future. So we use the diamond to express this here. So we can think of the diamond as being an inductive type like this, right? Which is either a value A now, or it is later a promise of a value of type diamond A. Right? So the problem is we cannot get a inductive solution to this type equation because we do have the guarded fixed point combinator fix, which will result in that we have unique solutions to such guarded recursive type equations. So as a consequence, the inductive solution to this equation will actually coincide with the co-inductive solution of this equation. Right? We definitely did not have in mind. We did want to have the inductive solution here. So this also means that if we would add a type like this to our system, we would not get the expected behavior. Right? We would actually be able to implement a server of this type that will never give a response in the future. So to add inductive types to our language, we actually have to tear apart again this nice coincidence that we observed earlier, right? Where we equated the triangle with the circle modality. So we distinguish between the two in our system. So we have our triangle modality for the guarded fixed point combinator, and then we have separately the circle modality purely to express temporal aspects. We still allow a map from circle to triangle, but not the other way around. And this will allow us to distinguish between those two solutions, the inductive and the co-inductive solution to the type equation that I've shown you earlier. Right? So we get this one here with the circle, which is our diamond A, which means that we will get a value of type A in the future, and we get this one here that uses the triangle, which is the type of events of type A, which might give us a value in the future, but not necessarily. So we have these examples here for these types. So we get our server type as expected. So given a request, the server will eventually come up with a response. But we can also model a mouse click as an event, right? Which, if the mouse is eventually clicked, then we get the position of the mouse cursor. But the user might decide never to click the mouse, right? So we might never get such an event. So now that I have presented our language Lively RaTT in very broad strokes, I would like to go a little bit more into the details of the language. So our language will ensure that there are no implicit space leaks. So memory is deleted after every time step. It will also ensure that all programs are causal and productive, and it uses a Fitch style of dealing with modalities, so the triangle and the circle. And this will allow us to avoid using pattern matching and let bindings for dealing with those. So this actually goes back to our previous work on the Simply RaTT language that we presented 2 years ago. And what we do here is we extend this with inductive types to express liveness properties, termination, fairness, and the like. And so the key ideas that make this work is, well, to treat those two modalities, the circle and the triangle, separately. In particular, to treat the circle as a submodality of triangle. And secondly, to actually prove the liveness properties, we use a cryptological relation that uses transfinite step indexing. Right? So cryptological relations are very good for proving safety properties, so causality, productivity, and so on. But so far, they have not been used to prove liveness properties. And to do that, we use transfinite indexing. So let me explain the core typing rules of our system. And actually, I will go back to our previous system, Simply RaTT, to explain the basics of the Fitch style approach. So the core idea is that we have these tokens, these ticks in context, that separate the context in stuff that happened before the tick happened and stuff that happened afterwards. So essentially, all the variables before the tick are available previously, and all the variables that are occurring to the right are available now. So this denotes the passage of time. And so if you want to construct a value, a term of type later A, you have to give a term of type A, but in a context where time has passed already, so where we have a tick. And vice versa, if you want to advance a later type, so you eliminate the later, so you have a term of type later A, you advance it to type A, you do that by consuming such a tick in the context, so it will go away. Right? And so this advance can only happen if you are in fact in the future, only if time has passed. So the same happens in our new system, Lively RaTT, but here we have two modalities, the circle and the triangle, and we allow both the delay and the advance for the two modalities. So delay is an introduction form for circle and the triangle, but then we annotate the token tick with the corresponding modality, circle or triangle. And then we can use, again, this token to eliminate the corresponding modality, but we also allow that the triangle can eliminate the circle, because here we consider the triangle to be more powerful than the circle, right? So here we allow any m prime that is bigger than m to eliminate this m, right? And this will allow us to have inclusions of the form circle A to triangle A, so we can turn circles into triangles, but not the other way around, which is important. As a consequence, we are allowed to convert, for example, the diamond into an event, meaning that whenever we have the assurance that eventually we get a value of A, we can convert this into an event that says we might get a value of type A, but we cannot do so the other way around, right? Which would be unsound. But operationally, the two modalities still have the same behavior. It's only at the type level. They are different. In order to prevent space leaks, we have to be very careful in not allowing values to be moved into the future arbitrarily. Right? So for example, we cannot allow this term to be of this type for any type S here, right? We cannot simply take any value x and then delay it into the future like this. So for example, if we choose S to be the type of streams over natural numbers, then this would allow to move any stream, any infinite stream, move it by one time step into the future. If we just allow this willy-nilly, this would immediately lead to space leaks. So instead, we will restrict this type here to stable types. So stable types are the unit type, natural numbers, and these are also closed under products and coproducts. And we can turn any type A into a stable type by using the box modality. And for introducing the box type, we have similar introduction and elimination rules that we already have seen for the circle and the triangle. Right? So if we want to box a term and like this, we introduce a new token, the hash token, into the context, similar to the tick token that we've seen before. And if we want to unbox a term, so go from a boxed type to unboxed type here, we have to consume this token, this lock token, from the context. Crucially, also the fixed point combinator as an introduction form for the box type. And that is because we want to allow the fixed point to be executed at any time in the future, right? Because we unfold the fixed point over and over again and thereby move it arbitrarily into the future. So it has to be stable. Okay, and finally we get to our inductive types. And here we consider the until types as sort of a good representative of that. And all the examples that we have looked at can be expressed using until types. And this is the until type, or the until connective, that is known from linear temporal logic. Right? So where we say a value of type A until B is essentially a finite stream that produces a bunch of A's and then finally produces a B. Right? Or on the type level, you can see this is either a value B now or a value A followed by a promise that in the next step you get a value of type A until B. And we take the inductive solution to that equation. And the introduction forms for these are essentially now, which is the left-hand side choice, and the wait, which is the right-hand side choice, right? Where you give a term S of type A and a term T of type later A until B. Examples are, well, we've already seen one. The diamond is in fact an until type, so diamond A is a unit until A, so we get a bunch of values of type unit until we eventually get our value of type A. But we can also express the type of fair streams over A and B. And you can think of this as a type of streams that produce values of type A or type B, but it will never starve either values of A or values of B. So it will never devolve into purely a stream of type A or purely a stream of type B. Right? So we start out with getting some values of type A, and then eventually we get a B followed by a stream fair stream that then starts with values of type B followed by A and so on. So they alternate between these two states. And for example, we can implement a function like this that takes two streams, a stream of A's and a stream of B's, and then interleaves them in some fair fashion, right? This example and other examples are also found in the paper if you're interested. So let's talk about the results that we get for our language. And these are operational results. So we have to talk about the operational semantics. So the operational semantics will rule out implicit space leaks by construction. This is an idea that goes back to Krishnaswamy's 2013 paper. And the idea is here that we have a big step operational semantics that describes how terms are evaluated in a single time step. Right? So right now the term T evaluates to value V, and it has access to a store sigma, so it can read values from it, but it can also store additional values in that, so that we get a new store sigma prime. And essentially the only thing you can interact with this store is by advance and delay. So delay, if we have a term delay S, this will add a new value to the store at some location L, and it will store the term S. So it creates a thunk in that store S, and advance will read that thunk from the store. So it will find the mapping L from location L to the term S, and will read that and then evaluate that S. And the store will come in three different forms. We have the null store, we have a store consisting of a single heap, a store consisting of two heaps. And depending on which state we are in, the different operations are allowed. So if we are on the null store, then no operations, so no delay in advance are allowed, because there's no heap to store or read from. If we have what we call a later heap, this eta L, we can store thunks there. Right? So these are things we store in the later heap, so they can then be executed later on. And then if we have a now heap, this thing here, we can load thunks that have previously been stored by delay there. Right? And this roughly corresponds to the different ways that we may have tokens in the context. So the absence of any token corresponds to the null store if we have a hash in the context that corresponds to this store, and if we have a tick in the context that corresponds to this store. So the operational behavior of a program over time is described by this small step operational semantics that describes how, as the program is executed, how it emits new values at every step. For example, here for a stream, right? So at every step, it will emit some value V that is the current value of that stream. And it does so by a transition between states that consists of a term and a heap. And it does so by evaluating this term to a value, which is in this case a stream. So it has a head, the V that will be emitted, and it has a tail, which is a thunk that can then be advanced when moving into the next time step. And importantly here, the evaluation happens with an empty later heap that can then be used to store thunks for later evaluation. And it also has this now heap here that is drawn from the current state that then can be used by advance to retrieve thunks and then evaluate them. And importantly, after this is done, the new now heap here is discarded entirely, right? So this data is gone. We only keep the later heap. So this makes sure that we do not hang on to memory implicitly, and all memory that is supposed to be available in the next time step has to be moved explicitly into the future. And we can do the same thing also for transducers, so functions from streams to streams. And here we have a different semantics that allows us to read values from the environment and then emit values into the environment. So these values are then put into the store so that they can be read by the program. And here the same thing applies. So since we are deleting after each step, the now heap, also these inputs, so this v here that we store here, will eventually, after each time step, will be deleted. Right? So they will not be retained in memory indefinitely. And we can prove that our language will ensure productivity. So whenever we have a term t of type box stream of A, we can run this term indefinitely. So we get an infinite stream of values v1, v2, and so on of type A. We'll never get stuck. For stream transducers, we get a similar result. So we have a term that produces a stream of B's from a stream of A's, and we have an infinite sequence of A's that we give it as input. We indeed get an infinite execution of the stream transducer, where each output is indeed of type B, and the whole thing is causal. So the results at time step 2 will only depend on input values of time step 2 or earlier. And finally, we also have liveness properties. For example, we can prove termination of the until type. So whenever we have a term of type A until B, then we can run it, and it will eventually result in a state that halts, where the value that is emitted just before halting will be of type B, and all values before will be of type A as expected. Get a bunch of A's, and the computation terminates with a B. And for the type of fair streams, we can indeed prove that we get an execution that produces an infinite number of values of type A and an infinite number of values of type B. So none of the two are starved. So to conclude, we have presented a functional reactive programming language that combines inductive types with guided recursive types. And the key idea to make this work was to distinguish between these two type modalities, the circle and the triangle, and to treat the circle as a submodality of the triangle. So the resulting type system will ensure causality, productivity, and allows us to express liveness properties in the form of inductive types. The operational semantics will, by construction, rule out implicit space leaks. It's impossible to retain memory implicitly over time. And we use a Fitch-style approach to deal with modal types, which allows us to get rid of let bindings and pattern matching to operate with modal types in a much more concise manner. For future work, we develop a language with many ticks. So this present work is restricted to a single tick in the context. So that means you only can program one time step ahead in advance. This is not so much a problem of expressivity, so you don't lose any expressivity, but in some contexts it's more convenient to have several ticks available, so you can essentially program many time step in advance. The problem is if you allow more than one tick, you immediately get into problems with space leaks. Even if you only have 2 ticks, you can implicitly retain memory for an arbitrary amount of time. Moreover, we also work on the intentional semantics of this language. So the idea is then to use such a intentional semantics to construct a logic on top of the programming language to reason about functional reactive programs. And ultimately, the goal of this intentional semantics is to construct a dependently typed language that integrates both the programming aspect and the reasoning aspect in one language. So this was sort of the goal of this entire line of work. So that's also where the name RaTT comes from. So the goal is to build a reactive type theory in the end.